Imagine standing on the deck of like a deepwater oil rig, right? You're staring at this massive steel drill, and it is just completely coated in baked-on, highly pressurized crude oil.
Oh, yeah. Just absolute industrial sludge, heavy grease, carbon, all of it.
Exactly. And for the better part of the last century, if you wanted to get that raw metal clean, it meant, well, putting a worker in a full hazmat suit.
Right, and unleashing a toxic chemical cloud that could literally melt your lungs.
Yeah. You just wanted the grime gone, and the environmental fallout was, considered the cost of doing business.
It was a very scorched earth approach to industrial cleaning, but that whole paradigm is being completely dismantled right now.
It really is.
We are looking at a chemical landscape today that presents a massive, almost impossible paradox to anyone familiar with traditional maintenance.
Okay, let's unpack this, because that paradox is exactly what brings us here today, Friday, June 19, 2026. Welcome to today's Deep Dive.
Glad to be here.
Our mission for you, the listener, is to explore a specific technical data sheet, a PDS, for an industrial product called JetLube, Easy Clean Liquid.
And this is a really fascinating document.
It is. We are going to figure out how massive, vital industries, oil fields, marine shipping, large-scale construction, actually clean up their most impossible messes.
While also navigating the extremely strict realities of modern environmental safety.
Right. And if you are looking at this document with us, the branding alone sets a very heavy-duty tone. There's this bright orange, bold, italicized JetLube logo stamped right at the top.
Yeah, it looks like the kind of stencil you'd see painted on the side of a massive earth-moving excavator.
Totally.
The visual language is purely industrial. I mean, it is actively distancing itself from anything resembling like a boutique household cleaner.
Right, and yet reading through that very first paragraph, the contradiction just stares you right in the face. In bold text, the product is marketed as a frac and rig wash. It's designed to chemically strip some of the most stubborn, adhesive organic deposits on the planet.
But in the exact same breath, it claims to be non-toxic, biodegradable, and ozone-friendly.
Yeah, it literally calls itself tomorrow's answer to today's cleaning problems.
Which is quite a claim.
It is. And honestly, my immediate instinct is to call bluff on the marketing department. I mean, if it isn't using the traditional highly toxic solvents that the industry has relied on for a century, how is it actually stripping baked-on carbon off raw steel?
Well, the document actually points us directly to the mechanism in the first section. It identifies the formula as an alkaline-based cleaner and degreaser.
Okay.
And it says it utilizes, quote, newly developed emulsifying technology.
So when I hear the word emulsifying, my mind immediately goes to, like, standing at my kitchen sink.
Right, the classic dish soap example.
Exactly. If I have a greasy frying pan, the grease and the tap water absolutely repel each other. But the moment I add a single drop of dish soap, the oil and the water are forced to mix, and then I can just rinse the whole mess down the drain. So are we essentially just taking that kitchen sink concept and scaling it up to the size of a commercial oil rig?
Well, what's fascinating here is that scaling it up is kind of an understatement, but the foundational mechanics are absolutely identical.
Okay.
An emulsion basically forces two immiscible liquids, meaning liquids that naturally hate each other, like oil and water, to interact and suspend within one another.
Right.
And the molecules in this specific emulsifying technology have two very distinct ends. One end is hydrophilic, meaning it aggressively bonds with water.
Okay, hydrophilic, water-loving.
Exactly. And the other end is lipophilic, meaning it seeks out and binds to oil and grease.
So it acts like a microscopic bridge, connecting the water from the worker's hose to the sludge baked onto the equipment.
That's exactly it. The lipophilic end burrows deep into the carbon deposit, while the hydrophilic end anchors itself to the surrounding water. So when the worker hits the equipment with a high-pressure rinse, the flowing water pulls the molecule, and the molecule physically tears the grease right off the surface of the metal.
I mean, I understand the physics of that bridge.
Yeah.
But I really have a hard time believing a souped-up industrial dish soap can handle the sheer violence of an oil field.
It sounds like a stretch, sure.
Yeah. It lists applications ranging from metal fabrication to marine utilities.
Yeah.
I mean, moving a thin layer of bacon grease off a nonstick pan is one thing.
Right.
But we are talking about highly polymerized carbon deposits here, and crude oil that has been subjected to extreme geological heat and pressure.
Oh, absolutely.
So can an emulsifier really do that kind of heavy lifting without a toxic solvent backing it up? Is it really tomorrow's answer, or is that just marketing fluff?
Well, the true innovation here isn't merely the fact that it creates an emulsion. We've had emulsions for a long time.
Okay.
The real breakthrough is maintaining structural integrity against those massive, complex hydrocarbon chains while remaining entirely water-soluble.
Right, because historically you needed the harsh stuff.
Exactly. For decades, the only way to break those intense polymerized bonds was to flood them with aggressive chemical solvents. Solvents that would literally dissolve the grease at a molecular level rather than just lifting it.
Which brings us to, I think, the most revealing part of this data sheet. The manufacturer spends a huge amount of real estate bragging about what they intentionally left out of the formula.
It's totally addition by subtraction.
Yeah, listen to this list of exclusions. It contains absolutely NO 1.1.1 trichloroethane, no fluorocarbons. It is completely free of acids, free of chlorides, free of phosphates.
It's quite a list.
It is. But why was the industry so reliant on things like trichloroethane in the first place?
Well, trichloroethane, often called TCA, was the undisputed king of industrial degreasing for a very long time. It was basically a miracle solvent.
How so?
You could spray it onto a massive gear assembly covered in thick sludge, and it would instantly dissolve the grease, and then it would just evaporate into the air within seconds.
Wow, just poof, gone.
Leaving the raw metal perfectly clean and dry. No rinsing required at all. And fluorocarbons operated on a very similar principle. Phenomenal, rapid cleaning power with zero residue.
And there's always that. But there's a massive hidden cost to that instant evaporation.
A catastrophic cost, actually. We eventually discovered that when TCA evaporates, it travels into the upper atmosphere and aggressively destroys the ozone layer.
Right.
And on a more immediate local level, these volatile solvents are severe neurological toxins.
Which completely explains the next major brag on this sheet. It proudly states it is entirely free of SARA Title III, Section 313, Part 372 listed ingredients.
Yes. The SARA list is a highly regulated federal registry managed by the EPA.
Okay.
It catalogs the absolute worst chemical offender substances heavily linked to severe environmental degradation, cancer, and chronic health risks for workers.
So the stuff you really don't want to be breathing in.
Exactly. If a facility uses chemicals on that list, they are subjected to strict, continuous emissions reporting and massive regulatory burdens. So engineering a rig wash that stays completely off the SARA list, that's a massive operational and financial advantage for any facility.
It's huge.
And the emissions don't even stop there. The sheet says it contains no TTOs, total toxic organic compounds, and it boasts exactly 0 grams per liter of VOCs, volatile organic compounds.
0.
Plus, the safety profile reads like a dream. Non-combustible, non-flammable, non-fuming, non-toxic.
That sounds perfect.
It does, but if you take away the TCA, the fluorocarbons, the acids, the chlorides, and all the volatile organics, I'm honestly struggling to see how this product actually functions in the real world.
I get that.
I keep coming back to this polite bucket of water. If it doesn't have the chemical aggression of a traditional solvent, why doesn't it just beat up and roll off the crude oil?
Well, we have to look closely at the physical characteristics listed in the document. These characteristics replace the mechanical action of those banned chemicals.
Okay, like what?
Take the VOCs, for instance. A volatile organic compound is a chemical that very easily turns into a gas or vapor at typical room temperatures. Right, that evaporation you were talking about.
Exactly. That evaporation is what gave TCA its magic, but it's also what gives traditional degreasers that dizzying, overwhelming smell that just hits your lungs the moment you open the drum.
Yeah, that classic chemical smell.
Because this JetLube product has 0 VOCs, its vapor pressure is incredibly low. The sheet lists it at less than 0.04 at 20 degrees Celsius.
Okay.
Furthermore, it has an evaporation rate of less than 1 when compared to butyl acetate.
Meaning it stays a liquid exactly where you put it. It isn't instantly turning into an invisible toxic cloud.
Right. The data sheet explicitly states it is non-fuming. Think about the reality of an industrial worker operating in a confined space.
Oh, man.
They might be down in the dark, unventilated hull of a marine shipping vessel, or climbing inside a massive fuel oil truck body to scrub the interior.
So deploying a traditional solvent degreaser in those environments is basically a lethal hazard.
Purely because the invisible fumes displace the oxygen and poison the air. This product eliminates that airborne threat entirely.
Right.
It also features an auto-ignition point of none to 500 degrees Fahrenheit and a flash point of none to 212 degrees Fahrenheit.
So it's not going to suddenly catch fire or explode if a stray spark hits it on a hot drilling rig.
Exactly. It replaces the aggressive, volatile, and highly dangerous chemical reactions of traditional solvents with a highly stable, non-combustible liquid state.
Okay, but we need a serious reality check on the actual numbers presented in this text, because the word biodegradable does not mean harmless.
That is a very important distinction.
You hear non-toxic and non-fuming, and the temptation is to think you could, safely wash your hands with this stuff. But there is a single data point on this sheet that completely shatters that illusion. The pH of this concentrated liquid is listed as exactly 14.
Yeah, and that single number is the mechanical engine of the entire product.
Right.
It is the key to understanding the sheer brute force required to clean a rig without VOCs.
And here's where it gets really interesting. For anyone who hasn't thought about the pH scale since high school chemistry, it measures how acidic or basic a substance is, running from 0 to 14.
Right.
7 is perfectly neutral. That's pure drinking water. Down near 0, you find powerful, tissue-destroying acids like battery acid.
Yep.
But as you climb up towards 14, you reach the absolute extreme end of the alkaline or basic scale. To put that in perspective, liquid drain cleaner, the stuff you pour down your bathroom sink that literally dissolves the hair clogging your pipes, typically sits around a 13 or 14.
Exactly.
We have all this safe, ozone-friendly, biodegradable marketing on page 1, but a pH of 14 tells a terrifying story about its raw, corrosive power.
This raises an important question, right? And the document doesn't hide the danger at all. It places a stark warning right in the text. In its concentrated form, easy, clean liquid could be corrosive to aluminum and its alloys.
I noticed that. And you look at the other physical specs, it has a specific gravity of 1.07, meaning it's noticeably denser and heavier than water. It has a viscosity of 4.5 centipoise, so it's a bit thicker than water, maybe like a very light syrup, but still highly fluid. The boiling point is 212 degrees Fahrenheit, right at water's boiling point, and it freezes at 28 degrees. It also has a vapor density greater than 1 compared to air.
Yes.
But that warning about aluminum seems like a massive Achilles heel.
Yeah.
How exactly does a biodegradable liquid eat raw metal?
Well, aluminum naturally forms a tough microscopic skin and oxide layer that protects it from the elements.
Okay.
But at a pH of 14, the sheer density of hydroxide ions in the liquid essentially acts like a chemical sandblaster.
Oh, wow.
It dissolves that protective skin in seconds and begins aggressively eating the raw metal underneath.
So if it's that destructive, why push the pH all the way to the absolute maximum? I mean, why risk eating the aluminum scaffolding or the ladder the worker is standing on?
Because the manufacturer intentionally stripped away all the acidic and toxic solvent options to make it environmentally safe and non-fuming. They backed themselves into a chemical corner. Crude oil and oxidized grease are incredibly stubborn, tightly bound organic compounds.
Right.
Without the dissolving power of TCA or fluorocarbons, they had to rely entirely on extreme alkalinity to shatter those hydrocarbon chains. A pH of 14 provides the massive chemical force necessary to physically rip apart heavy oil field grease.
It's the ultimate trade-off. You lose the toxic fumes that poison the worker's lungs, but you gain a liquid that can dissolve the equipment if deployed incorrectly.
Exactly. Which brings us to the operational core of the document.
Right.
If a pH of 14 is powerful enough to eat aluminum, how do they actually use it safely? The dilution process outlined in the second half of the sheet is not a suggestion.
Yeah.
It is the absolute non-negotiable science of using the product without causing catastrophic damage.
And the mechanics of that dilution process are fascinating. The standard mixing method they outline is taking a 5-gallon pail of the concentrate, pouring it into a large industrial drum, and then filling the rest of the drum with water. And it notes you can use ordinary tap water or even salt water.
Though it explicitly mentions in parentheses that salt water comes with a reduced effect.
Why is that?
The heavy presence of dissolved minerals and sodium chloride in seawater chemically interferes with the efficiency of those emulsifying agents we talked about earlier.
Oh, acoustic.
Yeah, the salt essentially blocks the microscopic bridges from forming between the grease and the water.
Makes sense.
Yeah.
But once you have it properly diluted with fresh water, the application methods are incredibly broad.
Yeah.
Parts degreasing, steam cleaning, ultrasound cleaning, or simply brushing it on and wiping it off.
Very versatile.
Yeah, and I was like acting as an investigator, going through these suggested dilution ratios, and there's a mathematical pattern here that completely shifts how you think about cleaning.
Oh, absolutely.
The scale changes drastically depending on the job. For heavy drilling and construction equipment, the suggested ratio is 1 part cleaner to 10 parts water. For washing the bodies of fuel oil trucks or just general cleaning, it stretches out to 1 to 40. But the section on high-pressure sprayers is where the math gets genuinely wild.
If we connect this to the bigger picture, the shifting variables in that specific section reveal a masterclass in thermodynamics.
Seriously, let me walk you through these numbers. If a worker uses a pressure sprayer at a moderate 150 to 300 psi with cold water, the dilution ratio is 1 to 50.
Okay.
But if you just heat that water up, the ratio drops to 1 to 100. You need half the chemical for the exact same job just by turning on the heater.
Right.
Then you crank the pressure up on the sprayer to 500 to 800 psi. With cold water at that high pressure, you're at a 1 to 100 ratio. But if you use hot water at that extreme 800 psi pressure, the ratio drops all the way down to 1 to 200.
It's incredible.
So what does this all mean? Heat and pressure are literally replacing the chemical concentrate. Why is the water suddenly doing the heavy lifting?
Well, what you are looking at is a universal mental model for all cleaning, whether you are washing a sedan in your driveway or degreasing a marine shipping vessel.
Okay.
To clean a surface, you have to break the physical and chemical bonds between the layer of grime and the substrate underneath.
Right.
And you can achieve that through 3 primary forces: chemical force, thermal force, or mechanical force.
So the concentrate, that extreme pH 14 alkalinity that represents the chemical force.
Exactly. The hot water introduces the thermal force, and the high-pressure sprayer provides the mechanical kinetic force.
That makes so much sense.
By drastically increasing the mechanical force, jumping the pressure from 150 up to 800 psi, and combining it with the thermal energy of hot water, you almost entirely eliminate the need for chemical toxicity.
Wow.
The kinetic energy of the water droplets hitting the surface at 800 psi physically blasts the bonds apart, while the heat lowers the viscosity of the grease, melting it and making it much easier for the emulsion to wash it away.
So by optimizing the physical equipment on site, a company can use 200 times less of the actual chemical.
Exactly. A 1 to 200 ratio means 1 single gallon of this concentrate creates over 200 gallons of highly effective cleaning fluid.
That is massive.
It saves the company an immense amount of money on purchasing, shipping, and storage. But more importantly, from an environmental standpoint, it exponentially reduces the chemical impact of the runoff going into the drainage system.
Right.
It perfectly aligns with their initial claim. By engineering a product that is highly reactive to heat and pressure, they empower the industrial sector to minimize its chemical footprint.
That is incredible. We started today by looking at a bright orange heavy-duty JetLube logo, right? Expecting a story about harsh, toxic chemicals melting away oil field grease in a cloud of hazmat fumes.
And instead,
we took a deep dive into the elegant mechanics of alkaline emulsification. We learned how intentionally banning miracle solvents like trichloroethane and fluorocarbons forced chemists to rely on extreme aluminum-eating pH levels just to break hydrocarbon bonds safely.
Right.
And we uncovered a universal mental model of cleaning, where cranking up the heat and kinetic pressure on a sprayer can stretch a single bucket of liquid to unbelievable lengths.
It really is fascinating.
Taking the time to understand these technical data sheets gives us such a clear, surprising window into how the modern world actually maintains itself behind the scenes.
It highlights the invisible, highly calculated engineering that keeps our global infrastructure running.
Definitely.
And yet, for all its massive industrial scale, for all the talk of offshore drilling rigs, extreme thermodynamics, and heavy marine utilities, there is one final, almost surreal detail tucked into the margins of this text.
Oh, what stands out to you?
Remember the sliding scale of dilution ratios we were just discussing?
Yeah.
Tucked right there in the list, right between heavy drilling equipment at 1 to 10 and fuel oil trucks at 1 to 40, there is a suggested dilution ratio of 1 to 30 for, quote, upholstery, interiors, carpet.
Wait, carpet? I completely missed that.
Yeah. It includes a very specific warning in all capital letters right below it. Test for color fastness before rinsing and wiping dry.
Oh, no.
Consider that for a moment. This liquid was fundamentally engineered as a heavy-duty frac and rig wash.
Right.
It was designed to chemically sandblast raw, baked-on crude oil off of industrial steel scaffolding using a pH of 14.
Yeah.
What exactly happens at a chemical level when a homeowner applies a 1 to 30 dilution of this exact same industrial heavy hitter to a delicate red living room carpet to get a stain out?
Oh, my God.
Does the emulsion bind to the synthetic carpet fibers the same way it binds to oil field sludge? Does that extreme alkalinity immediately strip the dye from the rug?
I mean, I wouldn't want to be the one to find out.
Right. It is a striking reminder of the incredible and sometimes jarring overlap between massive industrial solutions and the mundane messes of our everyday lives.